All right, so section 8.4, that's our last section for chapter 8. We want to find the area K of the triangle with the side length A is equal to 3, side length B is equal to 4, and the angle measurement C is equal to 40 degrees. So finding the area for K is very simple. In this section, we were given the formula for K. So we just want to use that formula. So we can use the formula. K is equal to 1/2 times AB sine of angle C, which we have each one of those values. So K is just going to be equal to 1/2 times A, which is 3, times 4, which is B, times sine of C, which is going to be sine of 40 degrees. Then you want to go ahead and put that value in your calculator. It does simplify it down to 6 times sine of 40 degrees. I'm plugging it into a calculator. We end up getting that this is going to be equal to 3.86 square units. Remember, if you find the area of anything and you are not explicitly given units, you always just want to write square units instead. So a very simple, straightforward problem. Section 8.4 really did just give a lot of different formulas for things that it wanted us to solve. So fairly simple section. All right, section 9.1, question 5, we want to know the point 7, pi over 4 can also be represented by what other polar coordinates? Now, we know that when we have a polar coordinate, it has infinitely many other polar coordinates, but for our case, we're just going to go ahead and just identify 3 different kinds that we can have. So we're going to identify 3 other polar coordinates. So if we want to identify 3 other polar coordinates, this means that we have to change our original polar coordinate into a new form that also represents the same point. And the way that we can do that is that we can add or subtract 2 pi from theta to get a new point that corresponds to 7 and pi over 4. So this is just simple 2 ways. This is with 2 pi. Remember, this is going to be the same thing for 4 pi, 6 pi, 8 pi, 10 pi, all the negative versions. So they're all the same. So this is how we get infinitely many solutions, but these are going to be 2 of them. So this means that we now take 7 pi over 4 and we add 2 pi. Simplifying this down, this gives us 7 pi over 4 plus 2 pi is the same thing, saying pi over 4 plus 8 pi over 4. So we get 7 and 9 pi over 4. Then we can also focus on subtracting 2 pi as well as adding 2 pi. So now we're going to take 7 pi over 4 minus 2 pi, which we know this simplifies down to being pi over 4 minus 2 pi. So we have pi over 4 minus 8 pi over 4. So we get 7 and negative 7 pi over 4. So these are 2 points. There is one other way that we can fairly easily find another representation of this polar coordinate that doesn't involve us now just adding integer multiples of 2 pi. We can say that we can also add 1/2 revolution, which remember is just pi, to theta, which is pi over 4, and replace 7 with -7. So you can replace whatever number you have with now its opposite, in addition to adding 1/2 of a revolution to theta. And remember, this is going to be, they're on the same ray, they're just pointing in a different direction. So if we do this, we end up with a -7, comma pi over 4 plus pi, which then simplifies to -7, 5 pi over 4. So those would be 3 points that also represent our polar coordinate. So just a very quick touch here. So remember, if we do have a polar graph, oop, that is the wrong color. Oops, all right. That was the wrong color shape here, but we'll get the right one in a second. So if we end up in a polar coordinate system where we have our polar axis here, and we go ahead and draw out, we'll say, to about there. And we draw out this line. And we can state that theta, which goes all the way around, is equal to 5 pi over 4. And so this line right here, this is going to correspond with our point. This is technically going to be 7, 5 pi over 4. So remember, following that same line, we can now state that we have this additional point that is also going to correspond with 7 pi over 4 is this -7, 5 pi over 4 instead. So we have our original line, which is then going to be our 7, 5 pi over 4. We continue on that line in the opposite direction. This now gives us -7, 5 pi over 4, which also corresponds to our original point, which was 7 pi over 4. So we'd say equal to 7 pi over 4. Just a bit of a visual representation there. Now in section 9.2, problem 6, we just want to name what you changed when testing for symmetry and then what each conclusion means. So remember, when we were testing for symmetry, we were testing for 3 things. Those 3 things being the polar axis, the line pi over 2, which also corresponds to our y-axis on a normal rectangular coordinate graph, and then also the pole, which we also know as the origin from rectangular coordinate system. So we test for 3 things for symmetry: our polar axis, our line pi over 2, and our pole. And what we do to check for each one of these things, remember, is that for our polar axis, we're going to change theta to -theta. And for each one of these changes, we just want to see if when we make this change, is it going to be the same equation as we started with? That is what we're checking for. And if it is, that does mean it's symmetric. And if it's not, it means that we don't know. So then when we have our line pi over 2, we would then change theta 2 pi minus theta. And then C, for our equation, is the same as it began. Then lastly, with our pole, we're going to change r to negative r. Or, so when checking for the pole, we have two options, so you really want to check both. We can say, or we change theta to theta plus pi. So those are the things that we would then test for. And now we want to know, what does each conclusion mean? And when we say each conclusion, just the conclusions of, is it successful or did it fail? So if the symmetry test is successful, then our equation is symmetric about that concept object. So it would be symmetric about that object. Those objects then being the polar axis, the line pi/2, or the pole. So those are our objects. If the symmetry fails, or if the symmetry test fails, then we can't determine whether or not it is symmetric. Which means it's going to be inconclusive. So a failure does not mean that it is not symmetric. It just means that we don't know. All right, so a bit of a concept question there. Remember, you do want to be brushed up on the vocabulary of each section and some conceptual questions as well about certain formulas and equations that you're going to be given. All right, section 9.3. We want to plot the complex number 6 times the square root of 3 minus 6i on the complex plane, and then we're going to write it in polar and exponential form. So we're given our equation, 6 times the square root of 3 minus 6i. We also have our little graph here, so we can go ahead and plot this point. But the first thing that we want to identify is that our complex equation, z, which is in this case equal to 6 times the square root of 3 minus 6i, this is also equal to x minus yi, which means that if we were going to correspond this with a rectangular coordinate system, we get that x is equal to 6 times the square root of 3, and y is equal to negative 6. Oh, sorry, that's a plus sign, so y is equal to negative 6. Now, to be helpful with graphing, we can go ahead and use a calculator to solve what 6 times the square root of 3 is going to be. And it is going to end up giving us a value of 10.4. So x is about 10.4. So we want to go ahead and graph that point. We can easily do this because our complex plane looks extremely similar to our rectangular coordinate system, or our xy plane. And all we have to keep in mind is that our x-axis typically is going to be our real axis, and our typical y-axis is now going to be the imaginary axis. So imagine that any value that you plot on the imaginary axis has an I attached to it. So in order to plot this point, all we have to do is find the x value, 10.4. which if we move down here, we could say it's probably about maybe right here. And then we go down until we get to -6. And there we have it. There is our point. Remember, this is the point 6 times the square root of 3, -6. Or as we recognize it in our form of z, we have z is equal to 6 times the square root of 3 minus 6i. So that is this point here. So we plotted our point. Now we want to write this equation in polar and exponential form. So starting with our polar form, we know that already that x is equal to 6 times the square root of 3 and y is equal to -6. But we want to solve for r. When solving for r, remember our polar form gives us that r squared, or just r, is equal to the square root of x squared plus y squared. Which in this case, x is 6 times the square root of 3 squared plus y, which is -6 squared. So solving for these values, we get the square root of, it's going to be 36 times 3 plus 36. And when we add these values together, we're going to get 144, which is equal to 12. So our r value is equal to 12. Then cosine, because remember cosine is equal to x over r, cosine of 6 times the square root of 3 over 12 is going to end up giving us the square root of 3 over 2. And then, sine of -6 over 12. So remember, sine of theta is equal to y over r. So we have -6 over 12 gives us -1/2. So plugging these values in gave us these new values for cosine of 6 times the square root of 3 over 12 and sine of -6 over 12. And now we just want to find the angle on the unit circle that would correspond to these values. So if we look at the unit circle, we can figure out that the angle in the unit circle that corresponds to these values is 11 pi over 6. All right, so we found everything now. Oh, I just threw my pen. We just found everything now to solve for the polar form of our equation here. So once again, we're going to write polar form again. And now when we write out our polar form, we have our value of theta, which is in between 0 and 2 pi. You always want to just make sure that that is correct. So what theta is going to be between 0 and 2 pi. So the angle that satisfies that is 11 pi over 6. We already know that r is equal to 12. So the polar form is given to us in z is equal to r times cosine of theta plus I times sine of theta. So this is going to be z is equal to 12 times cosine of 11 pi over 6 plus I times sine of 11 pi over 6. And now remember we want to write our exponential form as well. So writing on our exponential form is now fairly easy since we already know what theta and r are going to be. And our exponential form is just stated as z is equal to r times e to the power of I times theta. So we're going to get 12 times e to the power of I times 11 pi over 6. And that would be our exponential form. So whether starting in exponential form or starting in polar form, we can figure out one or the other fairly easily once we already have one. So, all right. Then our last question here from section 9.4, problem 8, we want to write the vector v in the form of ai plus bj given its magnitude. Magnitude of v is equal to 4, and the angle it makes with the positive x-axis, which we are calling alpha, equaling to 150 degrees. So in section 9.4, we are actually just given a equation that would allow us to solve for our vector v given these items. So we can use the formula. Your vector v is equal to the magnitude of v times cosine of alpha I plus sine of alpha j. And since we have our magnitude and we have our angle, we can go ahead and solve this fairly easily. So we have v is going to be equal to 4, that's our magnitude, times, and now we have cosine of 150 degrees times I plus sine of 150 degrees times j. So we can use a unit circle or calculator if you want to find the value of cosine of 150 degrees and sine of 150 degrees. So once you do that, you end up getting that cosine of 150 degrees is going to be the square root, the negative square root of 3 over 2 times I plus sine of 150, which is going to be 1/2 times j. And then we just simplify. So our vector v is going to be equal to negative 2 times the square root of 3i plus 2j. And that would be our vector in the form of ai plus bj. So for this problem, we already have a formula for these things, so it's very easy to just plug these values in there. So, all right, that does conclude our review for chapters 8 and 9 for exam 3. Remember, there is going to be a review session for the Math Center at 9 in the morning, as well as I have my office hours, so feel free to stop by those at any time as well. So, all right, that concludes our review, and I will see you all again in our next chapter.